welcome to today's lecture. Today we are going to talk about the motion of falling objects, taking into account air resistance, also about linear momentum, and thirdly about the conservation of linear momentum. Now let's go to the first point, which is motion of falling objects with air resistance. This is quite complicated. So it is advisable to look back and remember what free fall was about, because that is easier. So free fall is the motion of an object as it falls. However, air resistance is negligible. The only acting force on the object would be the weight, and we neglect any air resistance. So if we are talking about free fall, the only acting force is the weight given by the mass and the Earth's acceleration, m times g. Now let's look at the equations which describe this movement. There we've got the equation for the acceleration. We see it is constant, given by g, so the acceleration does not change if we are talking about free fall, where the weight is the only acting force. Now integration of this equation gives us an equation for the velocity. Y dot, the velocity, given by g times t. Now the integration constant is 0 here, because if I put my time 0 at this time when I actually let drop the body, okay, so when I imagine you've got your body in your hands, and the moment you let go, the moment you drop the body, that would be t equals 0. So the moment you drop the body, the velocity is 0. This is the initial velocity. So if I integrate the acceleration, I arrive at y dot equals g times t with a 0 initial velocity. Now what we may notice here is that the choice of our coordinate system is such that the y-axis points downwards. So here's the y-axis, it points downwards in the same direction as the body falls. Here is the unit vector Ey pointing in the positive y direction. So this is why here the acceleration is positive and also the velocity is positive, because the velocity points in the same direction as the y-axis. Now let's accelerate. Now let's integrate the velocity again, and then we arrive at an equation for the distance. So after some time t has passed, the object is at position a half gt squared. Again, the integration constant is 0. If we say at time t0, the position is 0, so the initial position is 0, which would be just the position where the object is at the moment we let the body go. At the moment we let go and we drop the body, okay, that is the initial position. Let's say the initial position is 0, so then integration of velocity gives us a half gt squared. What we may note here is that these three equations do only depend on t. They do not depend on the mass of the object. So for objects falling through vacuum or through air, but with the air resistance negligible, then the mass actually doesn't play any role at all. All bodies, no matter whether little mass or big mass, they all fall down at the same rate. So the velocity increases at the same rate, no matter of the mass. However, it is not always advisable, not always appropriate to neglect the air resistance. Just imagine a very large object but very little in mass, like a balloon, a very large object that wouldn't fall like a very small object of the same mass. So a very little small ball and a very large balloon, they move downwards differently. So for some objects we cannot neglect the air resistance, whilst for other objects we may be able to do that. So today we want to talk about the motion of a falling object, taking into account the air resistance. So we consider objects moving at high speed through air. Again, here our coordinate system. The y-axis is pointing downwards. This is our object that we consider. The weight pulls the object downwards. The weight is given by m times g. Now, if we consider the air resistance, here we see it. It is given by, it's somehow given by v squared. So what we must remember here, that the air resistance, the force, the resistive force, is proportional to the square of the velocity. So for objects moving at high speed through air, the resistive force is proportional to the square of the velocity. This is very important. This we must remember. The resistive force I call friction force. It's a friction force, and it opposes the movement. So whilst the weight pulls downwards, the resistive friction force points upwards because it opposes the movement, and it is proportional to v squared. The friction force is given by a half d rho a v squared. Let's not consider the factor here first. Let's only consider the velocity for now. So you see the velocity of the object is squared. So the friction force is proportional to the square of the velocity. Now let's look at this factor here. What goes into this factor of proportionality? It is d, the drag coefficient. It is rho, the density of the air, and it is a, the cross-sectional area of the object, perpendicular to the direction of movement. So v is the velocity of the object. D is a drag coefficient. The drag coefficient is a dimensionless coefficient, a dimensionless entity, which takes into account the surface of the object but also its shape. So shape and surface go into the drag coefficient. The larger the drag coefficient, the larger the friction force. Rho is the density of the air. Again, the larger the density, the larger the friction force. And A is the cross-sectional area of the object perpendicular to the velocity. Again, the larger the cross-sectional area, the larger is the friction force. So what is the cross-sectional area perpendicular to the velocity? If you think in 3 dimensions, here this would be the cross-sectional area of the ball, which is perpendicular to the direction of movement. Now, if I've got a paper plate, for example, and I put it like that, then it's got a very large cross-sectional area. However, if I put the paper plate like that, it's got a very small cross-sectional area, and the movement of these two paper plates would be different. Whilst the paper plate being like that would fall down very quickly, and we could probably neglect the air resistance completely because the cross-sectional area is just so small. However, here, for the plate being like that, I would not be able to neglect the friction force because the cross-sectional area is very large. Now here the resistive force given as a half d rho a v squared, opposing the movement. That's why it's pointing in the other direction. Now we've got two forces. We've got the weight here and we've got the friction force there. If we've got two forces acting on one object, we have to add them up in order to find the net force. So here we've got the net force given as the sum of the weight and the resistive force. The resistive force has got a minus here because it's pointing in the other direction. So here we've got the net force again. We must remember that the friction force is proportional to the velocity squared. So at the moment when I actually let drop the body, the velocity is first 0 and then it increases. So to start off with, the velocity would be very small. However, as time goes on, the velocity increases, and as the velocity increases, so the friction force becomes larger. And so if the friction force here becomes larger, then the sum here, the sum becomes smaller. So the friction force becomes larger as the speed of the object increases. So now, please look at the friction force here. Yeah, it's coming now. See how the friction force increases. First the velocity was small and the friction force was smaller. Then the velocity increased and the friction force increased. It increases as long as the friction force is smaller than the weight. However, when the friction force is equal in magnitude to the weight, then the net force is 0. Can you see that? If the friction force is equal in magnitude to the weight, then the net force is 0. So the friction force becomes larger as the speed of the object increases until the friction force is as large as the weight. And if I take away the friction force from the weight, then I arrive at 0. So this means there is no net force acting on the body anymore. What happens then? No force acting on the body. Well, force is defined as mass times acceleration. Force equals mass times acceleration. Now force equals 0. That means 0 equals mass times acceleration. Now mass cannot be 0. Mass is just constant. However, the acceleration has to be 0 then. So if the net force is 0, this means there is no acceleration. Now no acceleration, can you remember? That means the velocity does not change. So if the friction force is as large as the weight, this means there are no forces acting anymore on my object which falls, and then there's no acceleration, and this means the velocity doesn't change. It's got a velocity which we call terminal velocity, and this velocity doesn't change anymore. The object continues to fall down with the same velocity. So the net force is 0. Another approach is to ask, what does the first law of Newton say about 0 net forces? So can you remember, what does Newton's first law say about 0 net forces? If there are no net forces acting on an object, it either stays at rest if it was at rest, or it continues to move in the same direction with the same speed. So here we are. Our object was moving downwards. It has reached its terminal velocity. So then there are no forces there anymore, no net forces. So we are here in this case. The object continues to move. The object continues to move. The object continues to move in the same direction with the same speed. So the friction force increases. First, the friction force is smaller. As the velocity increases, so the friction force becomes larger as well. The net force at the same time becomes less until the net force is 0. So when the net force has reached 0, then the object has reached its terminal velocity. The terminal speed is the speed that the object keeps whilst it is falling down. So first the velocity increases until it reaches terminal speed, and then the object just continues to fall down with this terminal speed until it hits ground. This is different from free fall, because for free fall the acceleration was constant, and so the velocity was always increasing. For free fall, the velocity increases constantly at the same rate until the body hits ground. If we have to take into account air resistance, then it is different. The acceleration is not constant, and the object reaches a terminal speed. So, if objects are moving at a high speed through air, they reach a terminal speed, and this terminal speed we may be able to calculate. So here we've got our weight, there we've got our resistive friction force. We know that the terminal speed is given for the case that the friction force is equal the weight. So this is a condition. Friction force is equal the weight, then the sum of these two must be 0. Yeah, or here just the same, weight equals friction force. Now if I take this equation times 2 and divide by d, rho and a, then I've got an equation for v squared. So v squared is given by tmg divided by d rho a. So the terminal velocity depends on the mass, but also on the drag coefficient, on the density of air, and on the cross-sectional area with respect to the flight direction. Now I can reformulate this equation and say the velocity, the terminal velocity, is given by the square root of 2mg divided by d rho a. Let's have an example. A raindrop has got a radius of 0.2 centimeters and a mass of 3.4 times 10 to the power of minus 5 kilograms. It reaches a terminal velocity of 9 meters per second. So the raindrop falls down from the cloud. The velocity becomes larger. However, at some point the velocity reaches 9 meters per second, and then the velocity doesn't increase anymore, but the raindrop continues to move downwards with 9 meters per second. A hailstone has got a larger radius of 0.5 centimeters and a larger mass of 4.8 times 10 to the power of minus 4 kilograms, and this one reaches a terminal velocity of 14 meters per second. And a skydiver with a cross-sectional area of 0.7 square meters and a mass of 75 kilograms reaches a terminal velocity of 60 meters per second, which is really large. It is 216 kilometers per hour. So these terminal velocities may be measured. Okay, we may just measure the velocity of the falling objects, or if we know all the input data, we may calculate it. So if we know the drag coefficient and the cross-sectional area, if we know the density of air, then we may just calculate the terminal velocity. Now we can also consider the kinetic energy. The kinetic energy of the raindrop, let's remember, is given by a half mv squared. So the velocity is 9 meters per second. We need to take the terminal velocity here, and the mass is 3.4 times 10 to the power of minus 5 kilograms. So a half times mv squared equals 0.0014 joule, which is very small. A raindrop has got a very small kinetic energy. Now the kinetic energy of a hailstone is a little bit larger, 0.047 joules. Let's look at the kinetic energy of the skydiver. It's got quite a large mass, 74.5 kilograms, and a large speed of 60 meters per second. A half mv squared equals 135,000 joules. This is a very large kinetic energy. So as the skydiver falls with a terminal velocity of 60 meters per second, the skydiver has got a very large kinetic energy. Very, very large. 135,000 joules. And this is also why the skydiver needs a parachute at a later stage. Because if the skydiver was to dive down and hit ground with this velocity, this would not be healthy. The kinetic energy of 135,000 joules is just too much for the skydiver to bear when he lands, okay? Because all this energy would be transformed into deformation energy. So the skydiver needs a parachute. A parachute makes a skydiver slow down because the parachute has got a much larger cross-sectional area, and the drag coefficient for the parachute would also be different. So once the skydiver establishes the parachute, then the kinetic energy would go down because the velocity goes down. And then it is actually safe for the skydiver to land. Now, let's talk about the other physical quantity I want to introduce today, linear momentum. The linear momentum is defined as the product of the mass and the velocity. The velocity is a vector, so the linear momentum is also a vector because a scalar times a vector is a vector. So the linear momentum is given as a product of mass times velocity, and it points in the same direction as the velocity. The direction of the linear momentum vector is the same as the direction of the velocity. Linear momentum is related to force. You can see that here. M times v, remember the linear momentum. Okay, if I take the time derivative of v, I have got acceleration a. So the time derivative of m times v equals m times a, and we know that m times a is force. So the time derivative of a linear momentum is a force. Whenever the velocity changes, then I've got a force. Of course, this relation here is only true if mass is a constant entity, if mass does not change. So force is given as the time derivative of the linear momentum. This is just another way of writing it. Again, another way of writing it. Time derivative of linear momentum. So it is a time derivative of m times v, which is m times a. And if the velocity changes, then a is not 0. And then we've got a force. So if the linear momentum of an object changes in time, then there is a force. And we can also say the force acting on an object is given by the rate of change of the linear momentum. So as the linear momentum changes, there is a force. A force means a change in linear momentum, and a change in linear momentum means a force. Now let's have these examples for our linear momentum. A raindrop has got a very small linear momentum of 0.00031 kilograms times meter per second. Now this is so small because mass is so small, because we need to multiply mass and velocity. linear momentum equals mass times velocity. So 3.4 times 10 to the power of minus 5 times 9 equals 0.00031, and the unit is kilograms times meter per second, because the unit of mass is kilograms and the unit of velocity is meter per second. The other example was a hailstone. It's got a linear momentum of 0.0067 kilograms times meter per second. And the skydiver has got a very large linear momentum of 4,500 kilograms times meter per second. Now here in this little drawing, I've plotted the velocity of the object which is falling. So the velocity points downwards. The object is still falling towards ground, and the velocity is given as the square root of t, the square root of 2 mg divided by d rho a. Now we must learn that the linear momentum of an isolated system is conserved. So before we had only been considering the linear momentum of one single particle or the linear momentum of just one object. However, now we are going to consider the linear momentum of an isolated system, where this is like the linear momentum of two objects which are interacting, two or more objects. Okay, an isolated system is something that doesn't interact with something else outside. So whenever two or more particles in an isolated system interact, the total linear momentum of this system remains constant. Whenever two or more particles in an isolated system interact, the total linear momentum of this system remains constant. So two or more particles interact, like two balls. For example, two balls, they are flying towards each other, they hit each other, and then they fly away in different directions. And they do not interact with something else. So they only hit each other. They do not hit anything else but each other. This would be an isolated system. There's no interaction with something outside. This is an isolated system, and so for an isolated system, the total linear momentum does not change. It remains constant. The total linear momentum is the sum of the linear momentum of all objects. So if I've got two particles, I need to sum up the linear momentum of these two particles, and I know that the linear momentum is always the same. It doesn't change. This is the principle of the conservation of linear momentum. The linear momentum of an isolated system is conserved. So here, this is my linear momentum of one particle, but I need to sum it up for all particles. Okay, so this here is a sum of all my linear momentums within my isolated system. So I've got two particles, so I need to sum up the linear momentum of the first one and of the second one. And now the law of the linear momentum conservation says that the linear momentum does not change for the system. So this sum here must always be the same. It mustn't change. Now, if I consider change, I can also consider the time derivative. And I know that the time derivative is 0 if the system does not change. So if the sum always remains constant, then the time derivative is 0. Like here, I've got my linear momentum of one particle plus the linear momentum of another particle. I consider the sum of these two. I sum them up. The sum shouldn't change. If I take the time derivative, then it is 0. Now let's have an example. Let's consider the elastic collision of pool balls of equal mass. Pool balls, this could be billiard balls, yeah? Pool and billiard is almost the same. Elastic means they hit each other and then they go apart again, so they do not stick together, they just hit and then they are separate again. So let's consider the elastic collision of pool balls of equal mass. By the way, if it is a perfect elastic collision, then we've got conservation of energy. So let's consider the linear momentum now. We've got two pool balls. One is here. This pool ball is flying. It is flying towards another pool ball which is at rest. Here's the other pool ball, okay? The blue pool ball here, that is at rest. It doesn't move at all. But this one here is flying towards this one and it's going to hit this one at some point. Now, however, let's consider the linear momentum of this pool ball here before collision, whilst it is still flying. This pool ball has got a mass, 150 grams, and a velocity, 32 kilometers per hour. The linear momentum of this pool ball is given by 0.15 kilograms times velocity. So the velocity I've transformed in meters per second by dividing the velocity in kilometers per hour by 3.6. So 0.15 times 32 divided by 3.6 equals 1.33. The unit is kilograms times meter per second. This is the linear momentum of the red pool ball as it is flying towards the blue one. The linear momentum of the blue one is 0 because the blue one is at rest, because the velocity of the blue one is 0. So before collision, the sum of the linear momentums is just given by the linear momentum of the red one, 1.33 kilograms times meter per second. Now, the sum of the linear momentums before collision must be the same as the sum after collision. So let's consider the linear momentum after collision. The red ball has hit the blue ball. What happens? And this is what we can see. The blue ball flies away, but the red ball stays put. The red ball doesn't move at all, while the blue ball flies away. Now the linear momentum of the red ball now is 0 because it does not have a velocity. The linear momentum of the red ball is 0 because it stops. However, the blue ball has got a linear momentum now because this one is propelled, this one flies away. It's got the same mass, and because it's got the same mass, it also has got the same speed as the red ball had before the collision. We can verify this by a simple calculation. Consider the linear momentum before and the linear momentum after. Remember to consider the linear momentum of the closed system. Always consider the total linear momentum. So here, linear momentum of red ball plus linear momentum of blue ball. And here before also, linear momentum of red ball plus linear momentum of blue ball. So before must be the same as after. Before, this one here was 0, and after that one here is 0. So this one must be the same as that one. The linear momentum of the red ball before collision must be the same one as the linear momentum of the blue ball after collision. Now we know that the masses are the same, so the velocity of the blue ball after collision is the same one as the velocity of the red ball before collision. Another example. A 60 kilogram archer stands at rest on frictionless ice and fires a 0.5 kilogram arrow horizontally at 50 meters per second. With what velocity does the archer move across the ice after firing the arrow? Let's visualize this. There's our archer. The archer stands at rest, and the archer holds a bow in his hands. The blue bow here. And in the bow there's an arrow. The archer wants to fire the arrow, however, before the arrow is fired, the archer, the arrow and the bow are at rest. At rest means zero velocity for all of them. Now the archer fires the bow. So the bow, not the bow, the arrow, the archer fires the arrow. So the velocity of the arrow increases from 0 to 50 meters per second. An increase in velocity means that there is an acceleration. An acceleration means that there is a force. So the archer exerts a force on the arrow in order to accelerate this arrow to a velocity of 50 meters per second. So there is a force in that way. In that direction there is a force, and this force I call action force. The third law of Newton tells us that there is a reaction force in this direction. The reaction force is equal in magnitude, however opposite in sign. So as a force is exerted on the arrow, there must be a force exerted on the man and on the bow in the other direction here. So it makes sense to ask for the velocity of the archer. Of course, it does only make sense if the archer stays on frictionless ice. So there is a force which will make the archer move into this direction here. If it was not on frictionless ice, like on normal ground, then this force would be counteracted by the friction force, okay? But there is no friction force. So because there is no friction force, actually, as the archer fires the bow, as the archer fires the arrow, so the archer is propelled backwards, according to the third law of Newton. So here we've got the action force. It is the force by the bow on the arrow. Then we have got the reaction force, which is the force by the arrow on the bow. And the third law of Newton tells us that the action force equals minus the reaction force. The action force is equal in magnitude to the reaction force, but it is opposite in sign, and this is why we've got a minus here. Let's reformulate this equation, and then we arrive at action force plus reaction force equals 0. Let's remember that a force is related to a linear momentum change. So whenever there's a force, the linear momentum changes. So here we've got a force, the action force, which was a force exerted by the bow on the arrow. So here we've got the force by the bow on the arrow, okay? And then we've got the reaction force here. No? So here we've got the action force by the bow and the arrow, and here we've got the reaction force by the arrow and the bow. The sum of these must be 0. So we need to be a little bit more precise. So we put in the mass of the man and the velocity of the man, and the mass of the arrow and the velocity of the arrow. Here we've got the same equation again. We know that the action force plus the reaction force must be 0. Let's now consider the linear momentums. Here we've got the linear momentum before the shot. There we've got the linear momentum after the shot. Remember, we must consider the total linear momentum of the whole closed system. So we must consider the total linear momentum of man and arrow. So here's the linear momentum of man before and the linear momentum of arrow before. So we sum these two up and we compare it to the linear momentum of both, of man and of arrow, after. And it must be equal according to the law of the conservation of the linear momentum. So let's put in our numbers. We've got a 60 kilogram archer. Initially the archer is at rest, and we are looking for the velocity that the archer assumes after firing the shot. We also have got a 0.5 kilogram arrow. Initially the arrow is at rest. After shooting it is at 50 meters per second. So before firing, the archer is at rest. The archer is at rest, so the linear momentum of the archer is 0. Also the linear momentum of the arrow is 0, because before firing the arrow is at rest. After firing, the linear momentum of the arrow here, let's look at that first, is given by the mass and the velocity. 0.5 kilograms times 50 meters per second equals 25 kilograms times meter per second. This is the linear momentum of the arrow after firing. Now the linear momentum of the archer after firing is given by the linear momentum of the arrow, because we remember the sum of the linear momentums after must match the sum of the linear momentums before. Before the sum is 0, so here the sum must also be 0, and this is why the linear momentum of the archer here must be equal the size but opposite in sign, minus 25 kilograms times meter per second. Now we know the mass of the archer, so now we can calculate the velocity of the archer, because linear momentum is given as mass times velocity. So here's again our equation. Linear momentum of man before plus linear momentum of arrow before is 0. This must be equal linear momentum of man after plus linear momentum of arrow after. This must also be 0. However, this one is plus 25 and that one here is minus 25. Let's not forget the units. So we know the linear momentum of the man and the bow. We know the linear momentum of the arrow both before shooting is 0. We also know the linear momentum of the arrow after shooting, 25 kilograms times meter per second. So we know the linear momentum of the man and the bow after shooting, which is minus 25 kilograms times meter per second. The velocity we find now, because this is what it is here, just the same. So the velocity is given by minus 25 kilograms times meter per second equals 60 kilograms times the velocity. Here we've got the velocity. This is just the definition for linear momentum. So the velocity is given as minus 25 divided by 60 meters per second. So the velocity of the man in the bow after firing is given by minus 25 divided by 60 meters per second equals minus 0.42 meters per second. This is a very small velocity, so whilst the arrow moves at a speed of 50 meters per second, the speed of the man and the bow after shooting is just 0.42 meters per second, which is less than 1% of the arrow speed. But we must note here that there is a minus sign here, and this minus sign tells us that the arrow moves in the opposite direction of the man in the bow. So while the arrow moves forward, the man in the bow moves backwards. Just a little bit, very slowly, but they do. Example 3. An astronaut of mass 60 kilograms is outside the spacecraft and at rest. She wants her physics book, which has a mass of 3 kilograms and which is thrown towards her with a speed of 4 meters per second relative to the spacecraft. What is her speed as she catches the book? So as the astronaut catches the book, she is propelled backwards, because the book has got a linear momentum, and linear momentum is conserved. So the linear momentum of the total system before must equal the linear momentum of the total system after. Here we've got the astronaut initially being at rest. The book flies towards the astronaut because it has got a mass and a velocity. It has got a linear momentum. Now the astronaut has caught the book, and the book and the astronaut move in that direction, and they do so as one particle. So we need to consider the sum of the linear momentums before, and this must equal the linear momentums after. After we only have got one particle. The linear momentum of the astronaut and the book is 1, because the book and the astronaut, they do not separate. The astronaut holds on to the book, so it is only one particle. So before we've got the linear momentum of the book, which is 12 kilograms times meter per second. We also have got the linear momentum of the astronaut, which is 0, because the astronaut is at rest. And we've got the linear momentum of book and astronaut after catching, and this is given by the mass of book and astronaut times the velocity. The velocity we want to find, that is easy. It is given by 12 divided by 63 meters per second, which is 0.2 meters per second. So the velocity is very small. We may note that the speed is positive, as was the speed here for the book. This means the astronaut is propelled in the same direction as the book was flying before. The book was flying that way, astronaut is flying that way afterwards. Let's have a summary. Today we've been looking at 2 things. One was the motion of an object falling through air at high speeds. If an object is falling through air at high speeds, there is a resistive force which is proportional to the square of the velocity. So this is very important. For objects moving through air at high speeds, there is a resistive force which is proportional to the square of the velocity. And because of this resistive force, the objects reach a terminal velocity. This is in contrast to free fall. So for a movement where we have to consider a resistive force, there the objects reach a terminal velocity. The other quantity we talked about was the linear momentum. It is defined as the product of mass and velocity. velocity is a vector, so the linear momentum is a vector also. The direction of the linear momentum is given by the direction of the velocity. We have also learned that the linear momentum of a closed system is conserved. So it does not change, which means the total linear momentum before an event must be the same as the linear momentum, the total linear momentum after an event. So the linear momentum of a closed system is conserved. It does not change. So this is the end of today's lecture. Thank you very much for your attention.